In part 4 of this video series looking at survival analysis with SPSS, we're going to turn our attention to the Cox Regression algorithm. Now, Cox Regression is what's known as a proportional hazard model, and it makes the hazard rate a function of categorical and or interval scale predictor variables. In other words, it can be used to measure how independent variables modify the overall survival chances of individuals. And as the name implies, what with it being called a regression, a method, it creates a predictive model that predicts the probability that the event of interest has occurred at a given time point for specific values of the independent predictor variables. Users who are new to Cox regression would benefit from familiarizing themselves with techniques such as logistic regression, as well as knowing a little bit about survival analysis and maybe looking at Kaplan-Meier beforehand. You should be aware that access to this procedure requires SPSS standard edition, or at least the advanced statistics optional module. Now, the Cox regression model actually consists of two primary elements. The first element is known as the baseline hazard function. We've already seen a hazard function earlier when we looked at Kaplan-Meier. In fact, we could graph it. And you'll remember that a hazard function shows the changing hazard rate over time. In this case, this baseline hazard function is baseline because it's independent of any predictor or independent variables that we may be using in the model itself. And the second element are the effects of those predictor variables, whether they be covariates or factors. The effects are expressed as actual coefficients, and their effects upon survival chance should be independent of time. These effects are expressed in a regression-like equation with coefficients, just like logistic regression, that actually modify the hazard function. Well, what do we mean by that? What we mean is that whilst the shape of the hazard function over time is determined by the baseline hazard, the covariates simply help us to determine the overall magnitude of the function, so it kind of shifts it to the left or the right. So while the baseline hazard is dependent upon time, the covariate effects should be the same for all time points. And that implies an important assumption about Cox regression. Now, earlier on we were talking about Kaplan-Meier. And in Kaplan-Meier we said that this is a non-parametric method. It doesn't really make a lot of assumptions about the data or about the distributions involved. Here we have quite an important assumption that relates to these two elements, but it relates to the baseline hazard function and the coefficients that are independent of that. This is known as the proportional hazards function assumption. And it basically states that because the model is comprised of these two separate components, one, which is a function of time alone, that's the baseline hazard function, and two, a function of the predictors alone, that's the actual coefficients from the predictors, it's reasonable to assume that the ratio of the hazards for any two groups is constant over time. So the predictor variables have the same proportional effect over time. It doesn't matter where you are on that time dimension, that the effect of being, say, male or female has the same effect, or the effect of being 1 year older than somebody else has the same effect over time. This is known as the proportional hazards function assumption. There are other assumptions associated with Cox regression are basically that the observations are independent of one another, that you're not including any irrelevant variables, you don't tend to have a lot of multicollinearity, very strong correlations among the predictors, and that you don't have too many extreme or outlier values that are going to affect things too much. In this example, we're using the sample data set telco.sav again. This is a sample dataset consisting of 1,000 rows of data, where each row represents a service subscriber to a telco company. The time to event variable simply records how long they've been a customer, the customer tenure. The event variable denotes whether or not they churned within the last month, so whether or not they cancelled their contract. There are lots of additional variables like gender and customer category. You'll find the file in the samples folder where SPSS statistics is installed, and you should bear in mind that access to this procedure requires SPSS statistics standard edition, or at least the advanced statistics optional add-on module. So once again we find ourselves looking at the telco.sav file displayed in the data editor of SPSS statistics. This time, however, we're not going to be using the Kaplan-Meier method. We're going to be using Cox regression. So we go down to Analyze, Survival, down to Cox regression. And again, we're going to specify a time variable and a status variable. These are the two key elements, and these are what are going to allow us to create a baseline hazard function. So we'll say, okay, what's the time variable? The time variable is months with months as a customer, basically months of service. That's the tenure variable. And then the event variable is whether or not that subscriber or customer churned within the last month. What indicates that they churned? Well, a value of 1 indicates that they churned, so we tell it that that is the event that we're interested in, code 1. And if we ask for plots here and said, okay, we'll have a hazard plot, that would basically give us a baseline hazard plot. If I then added in another variable here, I could add in a covariate. I could add in a predictor field or an independent field, just as if it was logistic regression. And in this example here, I'm going to just create a really super simple model and use one little variable here as a covariate. I'm going to use the variable retired. Now the variable retire or retired here is one which is effectively a dichotomous. It's binary. It's only got two values, 0 and 1. And technically speaking, I don't have to do anything at this stage. I don't have to tell it that it's a categorical field. The categorical setting up here is usually used for when we have a nominal field or a field with multiple categories, but when they're already binary, we don't need to use them. In this case, I am going to tell it that retire should be treated as a categorical variable, because I want to have control over what is called the reference category. The reference category is when a coefficient is produced for this, what is it referring to? Is it referring to the yes or the no? Or it's effectively a contrast. And I want it to refer to the last value, the higher value, which is the yes group. That means the coefficient that I get will show me the effect of not being retired compared to being retired on your chances of churning. Otherwise, it would show me by default the effect of being retired as opposed to not being retired on your chances of churning. And for this example, it's just easier. It's just easier to explain the output if we make the retired group the reference category. Now that I've added that in, I could actually go back to my plots here and say, by the way, you're doing a hazard plot for me. Why don't you give me a hazard plot where you've got separate lines for retired and non-retired people? We'll click continue at that point. You'll see the output it generates, and then once again we'll go to the slides and just work our way through the output to interpret it in detail. Click OK. There's the output being generated. You see a case processing summary. You see some stuff here with categorical codings. You see something called a -2 log likelihood value, omnibus tests, variables in the equation. This is our coefficients table, and then some values just showing us average values, mean values here. And we have our hazard function, overall hazard function, and the hazard function for the retired group and the non-retired group. Let's just look at this in detail and work our way through it. So looking at the regression output, the first thing that we encounter is the case processing summary, something that's pretty common in SPSS, simply telling us that 1,000 cases were entered into the procedure. And of those 1,000 cases, 274 of them experienced the event. In other words, 274 of them cancelled their subscription. They are churned. And so hence 27.4% is our churn percentage. The next thing that we see is a categorical variable codings table, simply reminding us that we set our only independent variable that we entered into the model, the retired variable, up as a categorical variable, and that we specified the yes group, the people who are retired, to be our reference category. So when we see a coefficient value, it will be in reference to that, meaning that the effect of not being retired effectively. That's what the reference category refers to. It's important to bear in mind here that there are only 47 cases, so it's not a very large group within the data set itself. The next thing we see is the model fit output, and it begins rather like logistic regression by showing us block 0, the beginning block. This is the model fit, or the lack of fit, if you like, with no variables, without any predictor variables entered into the model. Now we only have one predictor variable, which is the retire variable, but it's saying that basically this is kind of the error that you get. -2 log likelihood is the error you get. You wouldn't interpret this directly. It is -2 times the log of the likelihood, but suffice to say that the smaller that number, the better the model fits the data, so that when we enter data, and here we have block 1 enter method, we've just got one variable, but we might have a whole bunch. But as we enter the extra variables into the model as predictors, we would normally expect this number to get smaller, and sure enough it does get slightly smaller. And then these fit statistics then simply tell us, these test statistics, these omnibus test statistics then simply tell you whether or not that's better than a model without those variables in it. And they're all statistically significant. The reason why they're all the same values is basically because we're not entering data, we're not entering variables in a step-by-step basis or in blocks. We've just entered everything in one go. And anyway, we only had one variable. So model error fit statistics, the reduced value is statistically significant after the predictor variable has been added. So we know that adding the retire variable to the model has a significant effect. It's the only variable that's been added in there. That's how we know that it's actually contributing to it. And that leads us to the model coefficients table, which shows us the effect of any independent or predictor variables that we've added into the model, whether or not they're making a significant contribution and how much they affect the risk, if you like, the risk of, in this case, the risk of churn occurring. So the coefficients table is made up of a number of different elements to it. The first thing that you get to is the B value or the beta value. This is the coefficient itself. It's the thing that's used in the regression equation. So if you wanted to type out the regression equation and you wanted to predict somebody's likelihood of churning at a given point in time, then this B value would be used as part of that equation. Now, we don't really interpret it directly, but we can say that it's a positive number. So we can say that the risk is increasing as you switch from being retired to non-retired, because non-retired is coded as 1 and retired is coded as 0 in our reference coding. And the next thing we get to is a significance test, which is simply saying, does this variable actually make a significant contribution to the model? And it's saying yes, it does. The value is less than 0.05. And then we get the really important value, which we're going to spend some time looking at. This is called the EXP-B value, or the exponentiated B value, exponentiated beta value. And it represents the change in risk or the change in hazard associated with a 1 unit change in the predictor. And it's a positive number here. It's a number that's greater than 1. If the value was equal to 1, if it was exactly equal to 1, this would not be significant, because it would say that it doesn't change it in any direction. It doesn't shift it, it doesn't halve it, it doesn't double it. It's saying the value here is 6.4, so you're 6.4 times more likely to churn if you're a non-retiree. Just hold that thought for a moment, because we'll zoom in on it and look at it in a little bit more detail. But suffice to say that this is quite a large value here, because the difference between being retired and non-retired has quite a big effect. Though bear in mind, of course, that there aren't that many retirees in the data. And the last thing that we see here is just this little covariate means table, which is just the average of the retired variable. Remember that non-retired people were coded as 1 in our model because we used the categorical coding, and we made retired people coded as 0, so that was our reference category. So it means when we take an average of that, given that there's so few retired people, it comes out as 0.953, which just means that 95.3% of the cases are non-retirees. But we should take a closer look at this exponentiated B column, otherwise known as the hazard ratio, because it's quite important. And as we know, the exponential B column represents the change in risk or the hazard associated with a 1 unit change in the predictor controlling for other covariates. So that's important. There might be other variables in the model at this stage, such as gender or age. This controls for their presence. So it takes into consideration that they're also part of the model. When the predictor is categorical and the indicator coding is used, exponential B represents the change in hazard when changing from the reference category to another category. So we know the reference category are retirees, the other category are non-retirees. As such, the exponentiated B is also called the hazard ratio, since it represents the ratio of the hazards for two individuals who differ by 1 unit in the predictor of interest. Again, bear in mind that this may not necessarily be a binary field like retired or not retired. It could be a continuous field like age. So a 1 unit difference could be the difference between 33 and 34, in which case the exponential B value could be quite small, but you know it's a small difference because it's a small number, because it's a relatively small difference in a variable of that type. So here the exponential B value for retired is 6.468. This means that all other things being equal, the hazard in churning is 6.5 times greater for those who are not retired than the hazard for those who are retired. So the non-retired people exhibit greater risk and shorter survival times. It's worth emphasizing, however, that this value, this exponential B coefficient for the retired variable, does not mean that non-retired people will churn 6.5 times faster than retired people, or even that 6.5 times as many of those subscribers will churn in a given time interval. Instead, it literally means that people who are not retired have odds of 6.5 to 1 that they will churn compared to retirees. And lastly, we can look at the hazard function shown as a chart. So we get the cumulative hazard function here, but you remember that we asked it to actually produce a hazard function chart for us, which was split by retired and non-retired people. So the non-retired people here are equal to the no group, and the retired people yes into the yes group. And we can see that, you know, there's quite a big difference in the cumulative hazard. We can see the cumulative hazard for the retirees is much lower over time than the cumulative hazard for the non-retirees, which are, by the way, the majority of cases, of course. But there is, you know, there's a significant difference there between them, so it's hardly surprising that that is a significant predictor of your hazard and your likelihood of churning at a given point in time.